Abstract data types consist of a set of values and a set of operations. So a common example is the integers. Values are 1, 2, 3, and so on. Operations, addition, subtraction, so on. Typical example of ADT. In most popular modern uses of ADTs, the values and operations have no state. So the values are constants. 1, 2, 3 are constants. The operations have no internal memory. So addition, subtraction, so on, has no internal memory. It means they don't remember anything in between calls to the operations. We can implement a stack as an abstract data type. The values are all possible stacks and elements of stacks. Operations, new stack, push, pop, and is empty. I remember the implementation we did. So these operations take 0 or more stacks as input and return 0 or more stacks and elements as output. So for example, here the push operation takes a stack and an element x as input and returns another stack value. So here's an example call. So I do new stack here, which returns nil, an empty stack. Then I do a push here, which puts a on the stack. Then I do another push, which puts b on the stack. So I have a stack with b on the top and a just below. So the stack here has 2 elements. If I then do s2 equal pop s, where s is the value I just calculated, I will return the stack which contains only a, and the top element x is b. The implementation we saw before of this is almost an abstract data type. So here's the implementation. Remember how it works? It uses lists, nil, x bar s, and so on to represent stacks. But this is not a data abstraction because the list is not protected. The lists are completely visible like we saw before. So the question is, how can we protect the list and make this a true abstract data type? And in general, how can we build an abstract data type with real encapsulation that's enforced? So we need a way to protect values. So to do that, we'll introduce a technique, an idea called a secure wrapper. So a secure wrapper consists of 2 functions, a wrap function and an unwrap function. So the wrap function takes any value x, an unprotected value like a list, and it returns a protected version w. And w, if you try to look at it, you will see nothing. W is completely opaque. It's hidden. And the unwrap function does the opposite. It takes a w and returns the original value x, which is hidden inside the w. So these 2 functions together can be used to protect and unprotect values. How can we understand this? Well, the simplest way to understand how wrap and unwrap work is to think of them as doing encryption and decryption. So wrap does encryption and unwrap does decryption of the value, and they use a shared key. So there is a key, a secret key, that is known only by wrap and unwrap and by nobody else. So that's how you can understand what they do. So for each abstract data type that we create, we need a new wrap-unwrap pair. Otherwise, the pair wrap-unwrap that works for one, you could use it to break open the encapsulation for another. So that wouldn't be right. So each abstract data type needs its own wrap-unwrap pair. So we introduce a function, a procedure, because it has 2 results, new wrapper, which creates these 2 functions, the pair unwrap and wrap, each time you call it, okay, with a new shared key. So each time you call new wrapper, it creates a new key and then builds a wrap unwrap functions based on this key. I'm not going to explain here how new wrapper is implemented. If you are curious, you can look in the book. It's actually not too complicated, and it does in fact use a secret key, which is called a name. But this is explained in the book. You can look at section 3.7.5 if you want to understand that. So now, with wrap and unwrap, we can implement a true stack abstract data type. So first we create a wrap unwrap pair, and this is created once when we define the abstract data type, and then we use this in our 4 operations for the stack. So new stack push pop is empty. So how does it work? Well, for example, new stack has to return nil. Well, we take nil. We can't just return nil, but we have to return a protected version of nil. So it's a wrap of nil. IsEmpty compares the value with nil to see whether the stack is empty. Well, it has to call unwrap on W and then compare to nil after. So a more complicated one, look at push. When you call the push function, it first calls unwrap of W. This returns a stack value S. Then it builds X bar S. And finally, it calls wrap on X bar S to return the protected result. So you can see also that we use local here so that wrap on wrap are hidden from the rest of the program using static scoping. So some final remarks on abstract data types. So they have a long history. They weren't invented yesterday. The first language implementing really well the abstract data types is called CLU. It was developed by Barbara Liskov and her students around 1974. This is only a little bit later than the first object-oriented language called Simula 67, which developed around 1967. And both of these languages strongly influenced all the later object-oriented language up to the present day. So for example, Python and Ruby have clear influences from both of these. These abstract data type languages, they support a protection concept. They have to encapsulate the abstract data types, and CLU specifically has syntactic support to make this really easy. In the example I showed you with wrap on wrap, everything is explicit. There's no syntactic support. But a real language designed for abstract data types would give you syntactic support to make this very easy. And a final point, many current object-oriented languages, they also support abstract data types. And for example, we will see that Java objects are in fact also abstract data types.